Hello, hello. Thought it was Thursday, 8:30. Tech generate. Sorry, maybe did you write this because yeah, I'm 2 minutes late. I'm sorry. I've tried to send some picture from my phone to the computer, but somehow it didn't work. Didn't work properly. I'm finishing the tweet to say that we are going live, and actually today we are going to break some polycarbonate parts. So I'm quickly finishing the tweet. Okay, with the link, and there we go. The tweet is sent out, and also, please, if you are, if you're on Twitter or any other social media, you can also share that we are live. You know, every Thursday 8:30. Feel free to share with a friend that we are here to talk about 3D printing. The more we are, the better. So I think the tweet is out now. Great. So let's see if a little bit more people are interested in breaking some polycarbonate part, and then the same as last time. I think it's the 30th. December 30th for most of you. Here is the 31st. It's New Year's Eve here, morning for us, and I'm really excited to break some stuff this morning. Actually, I think that would be the first time that I do the experiment we did with the PLA, but this time doing it with polycarbonate parts. And I also have another small experiment. So it's just like how to understand a little bit more polymers. So it will involve like just some plastic, like plastic bags. There's different kind. If you have like some nylon bags as well, it can also work. But we will do a very small like manual experiment, so you can feel polymer alignments, and you can feel. We never see the actual polymer, right? But with this experiment, you will really be able to see what's the polymer. So just to make sure, is there tech generate? If you're still here, can you please confirm that everything is okay, like the sound and the video should be fine. I mean, that's the fourth stream now. Should be fine. Chris Polk, did you do any PCPBT? I'm very curious about that blend. Yeah, we have this one. So we have, when it comes to polycarbonate, we have the Polymax PC. So that's a top version of polycarbonate. We have Polylite PC, which is a more regular polycarbonate, comes in transparent. We have a PC ABS blend, more for processability. And we have a PC-PBT blend. So the advantage of PC-PBT that comes from the PBT compared to PC is the chemical resistance and the low temperature toughness. So at minus 30 degree, you keep up to 70% of its toughness, rather than regular PC at minus 30 degree will be around like half or less than half of its impact strength. So any polymer becomes very brittle at low temperature. So that's one of the advantage of PC-PBT. So yes, we do have one. And the idea today is to just to play around with these samples and try to break them and see how they break. Do they break in a do they shatter? Like, are they very brittle when they break, or do they just bend? We did the same in our last stream with the PLA. I'm not sure if you were here in the last stream, but we did all our PLA series, and we had a couple of surprises. Some of them didn't want to break at all. Like, I could spin them, I could bend them, and they wouldn't let go. So I'm wondering if there is any of them that would break in similar way today, or they would just all shatter, or maybe I might not be strong enough to break some of them, which I doubt, because they're pretty long. So with the leverage effect, I think it will be pretty easy to break them all. So maybe we can start by breaking these, and then like try to think a little bit about how they would behave, and then just try, and then after that we can go to the polymer test. You know, how to feel, how to align the polymers, and then feel the how do you call that? You know, the hydrogen bond between the different polymers. But we can go more into the technique for that one. Okay, so let's try to break a little bit some of the PC part. And so the first one is going to be Polylite PC. So Polylite PC doesn't have any nano reinforcement technology, so which means we haven't enhanced its impact resistance. And it has a very, very high modulus, so it's very hard to bend. And my guess is for this one, my guess is it's gonna break very sharply. So I'm gonna arrive maybe around here, and I think it's just gonna break. I don't think there will be pieces flying everywhere. I think it will just break in two pieces, and it will break around the middle. But that's my guess. If you have some guess, you can put it in the chat, and then we can compare. We can compare with the experiment. So let's go for the Polylite PC, and let's see how it will break. So I forgot again my safety goggles, but I don't think we printed these without 100% infill, so it's most likely 20%, 15% to 20% infill. I don't think it will shatter, but let's have a try. So that's for the Polylite PC. So I'm bending it. So now it's feel like Polylite PLA, and from that point I put a lot of force. Now I can feel, compared to the PLA before, now there's a lot of energy that comes into that. Yeah, much more than PLA. Like if it break at this point, then well, it's still not breaking. I'm putting a lot of energy. I'm definitely putting a lot now. I don't know if you can see my fingers squeezing on the plastic. I feel it's gonna break. Oh, whoa, okay. Well, not at all what I want. Let me bring some of the parts. So basically, it just shattered in many pieces. Very, very interesting. I mean, none of the PLA had done that. Even the Polylite PLA. I'm very surprised. I'm very surprised. So basically, what I have left is these two is this two part here. I don't know if there's maybe a little bit too much light, so that you can see properly. Let me do that. Yeah, is it better? So yeah, I only have these two, so it's transparent. So it shattered into 1, 2, 3, 4, 5, and 6 parts. So yeah, it shattered into 6 parts. So that's how, and I put a lot of energy in order to break it. So the next one is Polymax PC. My guess is, well, I was completely wrong with the Polylite PC, but I guess for Polymax PC, what's gonna happen is the same thing at the beginning. I think I will have difficulties to bend it to a certain point, but I don't think it will shatter. I don't think, like the first one, I knew it would just break very sharply, but I thought I didn't think it would break in so many parts. But this one, I think it's gonna bend all the way. I think I will be able to touch the 2 point, but it's just gonna be very, very hard to arrive to that point. But I doubt it's gonna break because of the nano reinforcement technology. So I think it's gonna be like Polymax PLA, just harder to bend. And I think with one more bend the other way, maybe it will break. At the opposite of Polymax PLA, where we could bend it multiple times. So let's try if Polymax PC would do this. So I would just bend it in the same way. So right now, I can feel it's a little bit easier than Polylite PC. And at this point, now I'm putting a good amount of energy now. So now, at this point, it's very similar to Polylite PC at this point. And I think around here, Polylite PC broke. So I think I'm already after the point of the breaking point of Polylite PC. And now it's very, very difficult to maintain this one. I think I'm gonna. Oh, okay. So it did break. It did break only on one side. You can see here. It did break on one side. So I guess if I go the other way, I think it will break completely. But it didn't. Well, let's see. I think yeah. Okay, so now there's only one small string, which I guess I can just kind of. Okay, there you go. So this part, the hi BV3D, how are you doing? We're breaking some polycarbonate parts. So not sure if you have seen the first one, but the first one basically exploded. the Polylite PC, but now that's the result of Polymax PC. So it didn't shatter at all actually, but it did break with the first bend with quite an amount of force. So I mean, we are only testing the bending strength, I guess, not the impact strength or the toughness of the material, but it's already interesting to see how they would break. So the Polymax PC very, very different from the Polylite PC. I'm printing a violin with Polylite PLA. Oh, interesting. I've seen. Is that? Oh no, it was a ukulele that I've seen on Twitter yesterday. I'm not sure how. I guess for instrument you need the material to have a very high modulus, right? So that I guess what makes the sound of the instrument is like the vibration of the case. Is that correct? So if you want something to vibrate, then you need the polymer to have a very, very high modulus. So I guess, and then it will vibrate more. Is that correct? So Polylite PLA, out of all the PLA, is the best choice, right? Because it's the one with the highest modulus. So that, yeah, just some quick thinking around the material for that application. Hovalin V5. Yeah, I'm not too much into violin, so I'm not too sure what is that? Is that a brand or is that a model? I'm curious how it sounds in different materials. Yeah, definitely. My guess is this. My guess is the higher the modulus, the better the sound. Like I mean, wood has wood is basically unbendable, right? If it doesn't absorb moisture. But that would be interesting. I may print one with PETG as well, just as a test. Yeah, let us know how it goes. Actually, the Polylite PC could be a good one because it's extreme high modulus. So I guess it should sound well. A polycarbonate violin, does that exist? Okay, so let's try the other one, which is the PC ABS. So for the PC ABS, my guess is that it's going to break exactly the same as Polymax PC. I think, however, I don't think I'm going to put as much effort to bend it all the way through. But let's try this. Let's try to bend. So the main reason is because the blend of ABS inside. ABS is a very ductile material. So I think it will the blend will bring this particular material a lot more ductility. So but let's try. Let's try to bend. Yeah, I can already feel it's very flexible. I mean, I don't feel the modulus, the stiffness that we had with Polymax PC and Polylite PC. So I'm bending it. I'm putting a little bit more force now, but still much less than the other one. Okay, at this point, yes. At this point, I think it's a little bit similar to Polymax PC. And now somehow it feels like gum. I don't think it's gonna break, is it? Okay, yeah, it doesn't. I can touch both. Yeah, it doesn't break. It look, nothing. I mean, it feels like a little bit like gum, and then it comes back to here. So not bad. Similar to, you know what? Similar to Polytera PLA. Well, even the Polytera PLA Plus. I think the Polytera PLA Plus bent all the way through and then came back around the same. But definitely, I think Polytera PLA Plus required a little bit less force. Again, it's just a feeling, right? Just with my hand. But that's what happened with PCADS. And if I go all the way back, yeah, it feels like gum, but maybe. Okay, so I have a fracture point now, similar to Polymax PC, and then I'm going all the way back again, and I guess it's gonna break again. No, still not. So oh, okay. Now there you go. Now I spin it a little bit, and well, I should be able to break it at this point. Okay, I think I'm getting there. Okay, so you can see it delaminated all the way. I mean, I basically have two sample parts at this point. And now, okay, now I get rid of it. So I end up with a big delamination here and a beginning of delamination here. Well, a fair amount of delamination already. So if we had to explain this, first, the gum feeling, I think, comes from the ductility that is added with the ABS. The delamination, my guess is because these parts were printed on the Ender 3, so no heated chamber, and this one requires at least 80-degree heated chamber. So my guess is the layer adhesion that comes from the entanglement from the polymers from one layer to the other layer. They need to stay in contact with a temperature higher than TG for a little bit longer in order to form this entanglement. So my guess is that it didn't have time to form enough to create a strong bond between the different layers. So that's why it just broke. But very interesting. Even Polymax PC didn't do like this. So this splintering that we can see here, we had the same with Polytera PLA. So it's very interesting. I wouldn't be able to explain why it's the same as Polytera PLA, but I think it's very interesting to see that. Maybe I would have to look at the molecular weight of this material. Maybe it has a high molecular weight, but I will need to check. So is that Loyal Moses? Is that the LM show? Hi, I'm so happy to catch the stream. Yeah, finally. Hi there, Loyal, long time no see. Distraction. Yeah. I think I joined your stream as Polymaker a couple of, is that a month ago or something like this? And then I wanted to join again, but somehow I don't know when you are live. I try to I'm very active on Twitter, but with the mention of Polymaker. So if you go live, then try to tag Polymaker, and then if I'm free, then I will join again. I really love your show, and I love what you're doing for the 3D printing community. So thank you very much for that. And destruction, yeah, definitely. Last time we destroyed all our different kind of PLA and see how they behave, and now we're destroying all our kind of polycarbonate and see how they do. Yeah, LM show. Okay, yeah, I knew it. So yeah, next time I really want to join again. I love this show, but and actually, the Polymaker Twitch only exists because of you. So we only use it for the LM show, which is interesting. I created it just for that. I will tag you for sure. Thank you very much. So the last one is PCPBT. So let's try to think a little bit. So PBT itself, I think, has similar fracture behavior as PC. So my guess is this PCPBT will behave similarly to Polylight PC, but it won't shatter in so many pieces. I mean, at some point, Polylight PC was quite dangerous, right? So if you do the same at home, please make sure you have your safety goggle on, because it shattered in like 4, 5, or 6 different small parts. But yeah, my prediction is that this PCPBT is gonna just break in 2 parts. So let's try. So I'm bending it, so I can feel already that it takes more. There's much more rigidity to this material than the other one, but less than Polylight PC. I would say in between Polymax PC and Polylight PC. Now, arriving at this point, it's much, let's say, similar to Polymax PC at this point. Yeah, I do think it's going to break. I think I can feel it's going to break, but I don't think it's going to shatter in many different parts. Right now, I'm putting a lot of effort. Yeah, there you go. So I think exactly as we predicted, and I think if I force a little bit here, I think no, not even. Yeah, I think the last part. I think I won't get the. Oh, there you go. So it also delaminated. So my guess here, like I explained, I think it broke as our prediction. And why it delaminated, I think the similar reason as PCABS. And actually, PCPBT required an even hotter chamber, like around 100 degrees, in order to make a very strong layer adhesion. I'm pretty sure I can delaminate this very easily. Yeah, look at this. And this was because it was printed on the Ender 3. So most likely it was printed with 260 maximum, or even if it was printed on the Ultimaker. Let me check. Yeah, no, I don't think so. But even if it was printed on the Ultimaker at 280, it's still not enough for PCPBT. But very interesting how it behaved, how it broke. So yeah, that's it for the different polycarbonate destruction test. So a quick summary: we have our Polylight PC that completely shattered in many different pieces. You can see here. I mean, it even started to break here. So very interesting. The second one was Polymax PC. It didn't shatter at all. It took one. It took 1 or 2 bend, I think, to break everything. Much more ductile than the Polylight PC. And then we have our PCABS that was very difficult to break. It requires a lot of bend, a lot of spin, a lot of pull, but it also delaminated all the way. So I guess for this material, it might be good for, let's say, small parts if you're printing on the desktop printer. If you're printing bigger parts, then you will require a heated chamber. And then our PCPBT, which broke almost the same as Polymax PC, but it started to delaminate also. I'm pretty sure I can also remove that part here. Yeah, you see? So this is very important to print at high temperature, around 300 degrees, and with a heated chamber. So not a material for all desktop printer. Okay, so that's for the polycarbonate destruction. Now we are going to dive a little bit more into the polymer technique. So, oh, Santiago, you made it. Actually, exactly when I'm going to start the test that we talked about. So glad that you were able to join. Maziri, love to watch your stream. Thank you very much. Maziri, I think you were the one last time that said that your husband just bought a 3D printer, right? You need to ask him to join the show so that we can we can learn together about 3D printing. And I highly recommend also the LM show. There is one in the chat called Loyal. So he also have a very nice show for people that comes into 3D printing and want to learn with the community. Okay, so why I have a plastic bag here, and let me check this also, the Creality manual, but I'm interested in the bag, not the manual. So what I want to explain here, it's a test that I discovered, I think last year, is a good way to understand polymers. So I was reading on most likely on Wikipedia. I was reading the problem of polymer alignment. So what happened is that if you, I think I was learning about necking. You know, these specimen, if you put it on a tensor strength machine, then at some point there will be a necking behavior where you will have like this curve here. And then I was kind of learning a little bit about this, like why at some point it's very easy to pull apart, like it's hard, then it's easy, and then it's hard again. You know, if you look at the stress strain curve. And then I was learning about this. And then what I learned is that at the beginning, it's a little bit hard to pull them apart because you have all the polymer that are a little bit like spaghetti, like cooked spaghetti. And then when you pull them apart, they just come this way, and then they slowly align all together until they reach that point. And then at this point, then it's much harder to pull the part apart because they are all stretched already. And then at this point, after you can put it more, then it will just break because they are all aligned. And then I was wondering, if they are all aligned this way, it means that at some point, if you do a force that is perpendicular to the very first one, then it should be very easy to pull everything apart, right? Because all the polymers are aligned this way. So if you have a force that is perpendicular, then you can just tear everything apart easily, and then you will have like a lot of strings. So what I did is I took a plastic bag. Okay, so if you have a plastic bag around you, just take one, and then we can do the experiment together. So you take that plastic bag. So I hope it doesn't make too much noise and you can still hear me. And then what you're gonna do is you're gonna pull the plastic bag, but make sure you don't break it. Just pull it apart. You see, you may have, depending on the plastic bag you're using, you will start to have stress marks. Okay? And then you take this stress mark and then you pull it a little bit more. Can you see? Yeah. Can you see the stress mark? Okay, and then you pull it more. And what you just created is polymer alignment. So in that region, all the polymers are parallel to each other, more or less. And then what you can do is you go perpendicular, and then you pull the polymer apart. And then you are going to feel, it's you really need to do the experience by yourself, but you are going to feel that there is no force. You basically pull everything apart. So if I do it one more time, I will try to align a big region so that you can see. So all of this white part, I'm trying to align all the polymers. I'm aligning everything. Okay. So I have all of this part that is completely aligned. And then I can change the alignment by pulling the other way. And it will be very easy. You see? And then now they are aligned this way. And now I pull the other way, and it's even easier. And then the other way. And then you can continue like this until you can see, like, you know, when you have like a chewing gum, and then, you know, the chewing gum, and then when you do like this and like this multiple times, and then it starts to splinter, right? You have all of these strings. Then you can have the same here, because what you're doing is you're aligning them and then separating them, and then when they separate, then they realign the other way, then you separate, realign, and then you do that again and again and again until all the polymers are, you know, very, very, I'd say, they are not entangled so much. And the thing when they are not entangled so much is that the strength of that part will be very, very weak. So that's why I cannot show you very well, but if I don't know if you can see, let me. It doesn't focus. Yeah, it doesn't focus very well, but hopefully you have a plastic bag around you, and then you can see in the middle. I cannot see the polymers, but I can see like the gum thing, and then that's how all the that's how you can feel how the polymer behaves. And when it comes to 3D printing, it's very, very similar. When you're actually printing, you are actually pushing the filament through the nozzle, and you are forcing, like the same way I'm forcing this way, you are forcing all the polymer to align. And that's why theoretically, if you take your part that you just printed and you try to separate them, I mean, it's impossible, right? But then it would react the same way. But another way to think about it is, if you have all of these polymers that are completely aligned, if you only print in one direction, then the force that would require to break that part perpendicular to the way you have printed it, then would be very weak. So that's one way that you can feel a little bit you can feel polymers in real life. It's a very interesting. I mean, I'm still continuing to separate all of them. I mean, I now end up with a very big one, and you can also notice the light reflect differently every time. That's because the polymer are never aligned in the same way. You see, I can continue until I have a very, very I'd say a very flexible, or like I don't know, a very thin plane of polymers. And then you can play around with this plane of polymers. You see, I can align them very easily, and then they become very strong in the alignment. And then if I go the other way, then it's very easy, and then I realign them. And then you can play with the light also, depending on how you align them. So very, very interesting. I don't know if some of you did try with some plastic around you. Yeah. Again, the LM show is called the LM show on Twitch. But you guys can try. I will try to. We have a microscope. So what I'm gonna do is I will try to post on social media a video of me pulling this and just checking what's happening under the microscope, and you will be able to see this what I'm talking about, because it's too hard to show you, especially that I have the big sun just near me. I don't have the LM show set up yet, but hopefully one day. But yeah, so I don't know. I really feel that it was the very first time that I can feel how the polymer behave just in front of me, right? Because polymer science is a lot of theory, right? And it's very hard to have actual experiments where you can see the polymer behavior, and you can feel it, you know, with your hand. You can experiment it. So I thought that was a very interesting test. So what? Oh, Santiago, you did. So what's your feeling? Is that you can do the same with a nylon bag, and usually nylon will be a little bit more interesting because it will stretch a lot depending on what nylon you're using, and the good. It works even better. You see, I just stretch the filament. I just stretch the polymer. I stretch it a lot, and then if I go the other way, I can, you see? Yeah, it's very hard to explain, but you have to try. You have to have that feeling where you basically control the alignment of the polymer, and it's just magic. I mean, I love doing this. You see, I align them here, and I can feel it. You have to try for yourself. Loyal, I'd love to see that under microscope. Yeah, I will try to get that shot. I think it would be very, very interesting. So that was mainly the test I wanted to show you for the last stream of 2021. We do have 20 minutes left. So do you guys have any particular question on on materials in general? We can even dive very deep into one of the problems you have with your 3D printer. I like to solve problems by looking at the root cause. The perfect example is warping. Warping, when people has warping problem, I see a lot of answers. That is, a higher bed temperature, glue stick, print slower, enclosure, this kind of thing. So these are great solutions. But what I like to do is when someone has a problem, like warping problem, I want to try to explain to them why they have a warping problem. Where does warping come from? And then after you have a complete understanding of the root cause of the problem, then the solution can come by yourself. You can find multiple solutions that solve that, because once you understand the root cause, then the solution is really the easy part. We can do, if you guys are interested, because I already explained a lot the science behind warping. So, but if you guys are interested in that, then we can dive again into that, so that you can solve your warping issue very, very easily. And you can understand why having a bigger nozzle solve your warping issue also. Does the chain align when the part creeps, or how does the creep process work? Let me think. So if we go back to the definition, so creep means so how the polymer will behave under constant stress. So if we are thinking about that plane, right, and then we just put some force on the wing. Oh, by the way, did you see all my planes here? This is to play around. It's very nice. Actually, Loyal, if you're still there, I think for 2022 gift box for Christmas, I think that would be a nice toy. It's the kind of toy you put the handle and then the elastic band, and then you just do like this. So it's printed with a lightweight PLA. But anyway, so creep. You would put a force here, a constant force, a constant stress, and then you will see how the polymer behave. So theoretically, I do believe that how the polymer will behave is that at some point, all the entanglement between the polymer will slowly release, and then they will slowly align. I'm not sure, but theoretically, yes, they should, because if they slowly entangle, detangle, or unentangle, then theoretically they will slowly align. So the answer for me is yes. From that explanation, I would say yes. And then my main problem is polyamide parts creeps. Polyamide part. What kind of nylon? Because if you have long chain nylon, let's say PA12, then theoretically you should have less of a problem compared to PA6 or 6.6. But that's just some theory. Chris Polk, all about temperature gradient from my understanding. Definitely love to hear your thoughts. Oh, you mean the warping? Oh, okay. So let's is that a public model? I guess so. I mean, we never removed the watermarks, so I can see 3z.com, THREEDSY.com. So that's the watermark. See, you can see it very well here. So that's the watermark on the model. So yeah, I guess it's public. So warping, but the 12 is the monomer, right? Not the length of the chain. I do think 12 is the number of carbon in the backbone, and then of the monomer, yes, and then you polymerize that monomer. So I do think, yeah. So your point is if the monomer has a longer chain, will in general the polymer be longer than PS6 that has polymerized? I thought so because of a white paper I read, but it's good to raise up this question again. It would need to be checked. You could have a short chain that is polymerized into a high molecular weight, and a long chain that is polymerized in a short molecular weight. So yeah, that's you have a good point. So warping, Chris Polk was talking about all about temperature gradient. I'm pretty sure he was talking about the warping, I guess, just that my message has a delay a little bit. But for me, I think warping does not come from Polymaker gradient. I've seen this explanation a lot, and I was wondering whether it is correct or not. So let's just go from that explanation and see why I doubt, why I had some logic problem with that explanation. So Chris Polk, let me know, Loyal, how much time left for the stream? We usually have like an hour 10 minutes, if that's what you were talking about. 12 the monomer I was talking about, the warping issue. So why I had some logical problem, because I think the explanation, and please Chris, let me know if I'm wrong, but I think the explanation that I've seen before was because you print the first layer first, and then second, third, blah blah, the first layer is going to cool down faster than the rest, and then so you will have some kind of gradient, because it will just it will always cool down before the other one. So why for me this is not very logical? First, because if you look at the data, the polymer basically cooled down so quickly that there is no much difference between the layers. So if you look at the part that you print, you may have this part that has a different temperature from all the rest, but all the rest are basically already at room temperature, depending on whether you have a heated bed or not. So that's the first part where I had issue, is there is no much of a temperature gradient anyway. The second part is, if there is indeed a temperature gradient, and if indeed that was the problem, then the bottom would shrink at a different rate as the top, right? Then theoretically it should warp the other way, because the first layer shrink a little bit, the second one shrink more, and then it shrink, and then it shrink. Then it would go this way, right? Because the first layer will shrink more than the second one, which is a little bit late, then the third one later, and then basically it will warp the other way. So that's the part that, you know, that's the logical part that I didn't understand. So instead of trying to go from there and trying to explain, then I just went back to the basics and tried to understand the warping behavior. So I just invited Twitter friend to come and watch. Yeah, thank you very much, Loyal. I think that's the perfect part, because we're going to dive into a warping issue. So I think that's great that more people can join to learn about warping. So again, this is only my understanding of warping, and each of us needs to have its own understanding. And the most important is that it's logical, and then it stick to our experiments, and it stick to our the experience we have with 3D printing. So for me, what's happening is that when you're printing, you have this pack of polymer, the spaghettis, right? And then you are forcing them through the nozzle, the die, and that's very, very small. So what's going to happen is, I wish I had a whiteboard, but the best is if you have 3D Print General book, then you can follow what I'm saying with the book next to you, and there is nice pictures. But what's going to happen in the die is you are going to stretch the polymer. Why does it stretch? Because when you're pushing fluid through a very small pipe, then there will be a velocity curve, right? The polymer that are in the middle will go faster than the one that are on the side, right? So what's going to happen is, if you have the pipe like this and you have the polymer, then that is like this, then the part in the middle will go faster than the part on near the edge. So this will align all the polymers, the velocity curve of your nozzle. So what's going to happen is, when you lay down the polymer on your bed or on the previous layer, then everything is going to be stretched, and the polymer doesn't like that state. It's like a rubber band. If you take well, I don't have a rubber band here, but if you take a rubber band and you stretch it, then whatever the temperature, it will just come back to its state. It's not a thermal thermal expansion. It's not the fact that you extrude at a high temperature so that it expand and then it cool down so that it come back. That's one type of shrinking behavior, but the shrinking behavior I'm explaining is an elastic deformation. So you basically push the rubber band through the nozzle, and then you stretch it, and then you just put it on your bed, and you put it in a stretch state, so it will want to come back. You can see Stefan video, CNC Kitchen, the YouTube channel. There is a very nice experiment where he tape a slightly elastic tape, and then he just tape one by one on the table, and then he just stick the tape on the table, and then he stretch it and then stick it, then take another one, stretch it and stick it. And as he does that, then everything start to warp. Why? Because each of the layer will have what we call an internal stress, and then it will start to warp. So how do you get rid of this? And also the warping, you can do the, each vector of the stress will basically form rotational vector. I really need a whiteboard. Loyal, you have to explain to me how you have all of these cameras and stuff, and what software do you use, so that I can have some kind of whiteboard here with a camera here, where I can explain with some kind of graph, because I only have 10 fingers to make my explanation. But let's do the why it shrink this way, and so it shrink this way, so why it would warp this way. So there you can do the calculation, but I won't do it because I don't have the whiteboard. But believe me that there is an explanation why you shrink this way and then you warp this way. And so how do you solve this? Well, what we just said is the root cause of the problem come from the stress you're putting in the filament, the stress that come from pushing the filament through the nozzle. So now there is a multitude of solutions to solve warping. The first one is, you can, let's go to the very beginning, which is the velocity curve. So you have to get rid of that velocity curve, right? The flatter the velocity curve is, and the less you are going to align all the polymers. So how can you make the velocity curve flat? Well, one way is to have a very big nozzle. If you have a very big nozzle, the velocity curve will look like this. Okay, will be a little bit flat in the middle. If you have a very small nozzle, then the velocity curve will look like this. And the sharper the velocity curve, and the more you're stretching all the different polymers, and the flatter or the more flat, how do you say? The flatter the velocity curve, and the less the polymer will align. So if you're printing with a 0.8 or a 1 millimeter nozzle, or even a 0.6, will always be better than a 0.4, a 0.3, or a 0.2. So that's one way. Another way, what goes into the equation of that velocity curve? Well, one part is the viscosity of the material. The more viscous the material, the more it will stick to the side, and the more there is a gradient, a velocity gradient between the middle and the side. So in order to improve that velocity curve to have a flat one, then you need to have a polymer with less viscosity. If it's a polymer with less viscosity, which means it's very liquid. You know, if you have honey into that pipe, then the honey will have a very high, a very sharp velocity curve. If you have water, then the water will just flow, and then the velocity curve will be very flat. So the viscosity, how can you lower the viscosity of the polymer? Well, you can print at higher temperature. That's why sometimes we recommend people to solve warping by printing at a higher temperature because of the velocity curve change. There is another part which we will talk after, but that's one of the reasons. Another way to flatten this velocity curve is to have nozzle that is coated with anti-friction material, and the anti-friction is going to make the material slide easier. So that means the velocity curve will also be flatter. So now you can think we already have three ways to reduce the stress. Well, we have one way to flatten the velocity curve, and in order to flatten the velocity curve, you have a couple of many different ways. And then for these ways, you may have different ways, etc., etc. But that's all about the nozzle. I'm thinking whether there is other ways. There is Stephanie, again, CNC Kitchen, that did some tests on how to heat up the polymer better in the nozzle. You know, he has like some different shape of nozzle. He put a copper wire into the nozzle. That's another way, because if you have equal viscosity, instead of having the middle that is colder than the side, then if you can have everything at the same temperature, then everything will have a lower viscosity, or similar viscosity as the one that is on the edge of the nozzle. But that's pretty much all for the nozzle. So that's already 4 solutions just for the nozzle itself. So let me do one quick pause here to see if there is any question. What happened? So Santiago, what happens to me after printing is that the top of the print cools faster than the part on the bed, so it warps after the print finish when cooling. Again, but that's not the question, because I still have a lot of things for the warping, but I will try to come back to this. I tried to pin on a warm oven as soon as they let it cool. Okay. Loyal Mosh, we are learning a lot. Yeah. Let's learn even more together. I had to pause as I'm listening, but you are correct in my question being about warping. Okay, great. But the rubber band heats up when you stretch it, and if you let it cool down, the force pulling it back decrease. It's quite amazing. Yeah. So the relationship between stretching and heating, I believe, come from the kinetic energy, which means depending on how fast you are stretching, then the temperature will change. I don't think it's only related to how far you stretch the elastic band related to the temperature. I think it's related to how far and how fast you are stretching. I think that's the relationship between stretching, temperature, speed of stretching, and the temperature. Okay, so not much question for the first part. So hopefully that was clear. So if we continue, the first was flattening this velocity curve. The second one is, let's say you cannot flatten the velocity curve, or let's say you still have stress after you extrude the filament. Well, another way is, how can you get rid of this stress after you print it? Sorry, I need to take a small break. Okay, so how do you get rid of that stress? So let's try to understand first, how does the stress accumulate? So you have this stretch filament, and then the problem is you are sticking it on something. If theoretically, if you're not sticking on anything, then it would be very easy for the material to get back to its let's say equilibrium state, because there is no other force that is forcing him to stay in that state. But the problem is you are sticking on something, whether it's the bed or whether it's the previous layer. So now you have stick, let's say, a cylinder of stretch polymer on top of another one. So how can you make sure that it doesn't shrink and deform your parts? Well, one way is to give enough energy to that polymer in order to release the stress without deforming the part. And in order to do that, you have to have the polymer that is above the glass transition temperature. So what's the glass transition temperature? Very quickly, you have a glassy state where all the polymer are frozen, and then after the the temperature is about vibration, right? It's how fast they are vibrating. And after the glass transition temperature, then the polymer are vibrating enough so that they can weaken the hydrogen bond between two polymer. You see, let's say this is one polymer, this is another polymer. Then why? I mean, these two polymers are not connected to each other, so theoretically they should just fall on the ground, right? But each polymer has a hydrogen bond, right? So you know that the dipolar molecule that are attracted to each other, like water, then there is a hydrogen bond. And then what happens is, if it's vibrating fast enough, then the hydrogen bond between all the polymer will be so weak that it's very easy for them to move around. But if they don't vibrate enough, then the hydrogen bond will be too strong for them to move around. And so that's the TG, that's the temperature at which the polymer vibrate enough so that the hydrogen bond is weak enough so that they can move. So that's the simple version of well, kind of simple version of the TG. So let's say you have stretched your polymer, right? So it's in the stretch state. This is my stretch state. This is my equilibrium state. So everything is stretched. So what happens is, if you give him enough energy, which means temperature, in order to move around without affecting what is around him, because the hydrogen bond will be weak enough, then it will be able to release the stress without affecting what is around him. So coming back to our cylinder that is frozen with so much internal stress, then this polymer will release the stress as long as it's above TG. So let's say you're printing at 260 degree polycarbonate. You're printing polycarbonate at 260 degree, and the TG of polycarbonate is 100. Let's say it's 100. So the time where the polymer will stay above 100, so you print at 260, and then it sharply go down to room temperature, which is, let's say, 30 degree. So that time between 210 and 100 degree is the time where it can release the stress. Okay? And the higher the temperature, the faster it can release the stress. So now that you understand this, you can try to think about how can we make that time bigger. And that's why we are talking about, oh, you need to use an enclosure. You need to use higher temperature environment. Why? Because what's going to happen is if you have a higher temperature environment, it means the cooling curve will be a little bit less sharp because it will go this way. Like, let's say the room temperature is here and the printing temperature is here. Then the cooling rate will be something like this, right? And then that means the time above TG will be that long. But if it's, I really need a whiteboard. But if the chamber temperature is this, then the cooling curve will be like this, right? So the time above TG will be much, much higher. And if you have the chamber temperature that is already at TG, then you can just get rid of any warping issue. You won't have this because by theory, the polymer will always be able to release the stress. So that's one way. One way is to increase your chamber temperature so that the cooling rate is less sharp, so you have more time to release the stress. Another way is you can extrude at a much higher temperature. If you have the room temperature here and you extrude here, then you will very, very quickly reach the room temperature, so not much time. But if you extrude, well, I'm out of the frame. If you extrude here, then there is more time for the polymer. Well, already if you extrude higher at higher temperature, we have the velocity curve that is flatter. But if you print at that temperature, you also leave a little bit more time for the polymer to release the stress. So that's another way to release the stress. Another way is to print at slower temperature. We are talking about the time, right? We are talking about the time it needs to release the stress. Where if you print at lower speed, then it will heat up the filament more, and then it will have a higher temperature when you extrude, so it will have more time to release. So you see, now you have all of these things that connect to each other. And for me, this explanation is, at least in my mind, is very logical. So the best is that, we kind of challenge each other to push that explanation even further. But in my opinion, this explanation, at least I can hold it in a discussion a little bit longer time that I can hold the explanation about the temperature gradient. So I hope, I hope that was clear for the warping. So let me see if there is any particular question. So there is much more people. So I guess that's thanks to a loyal tweet. Thank you very much for inviting more people in our very last 2021 live stream. Every Thursday 8:30 we are live streaming from our Shanghai office. Hi, no, I missed the start. Non-fam, yeah, I recognize your name. I think you were there. We actually did some destruction with some PC parts. Loyal Mo, do you get a stronger polymer chain with higher temperature? Not really. So the polymer chain is so the strength of the polymer itself is intrinsic to the polymer. So we were talking about many polymers, right? And then what happened is there is two kind of bonds in this. There is the primary bond. The primary bond is in the backbone of the polymer itself. So that's a covalent bond. So that's like a very strong one. The second bond is from a polymer to another polymer. There is some secondary bond, which is the hydrogen bond. So by printing at higher temperature, it won't affect the bonding between the molecule itself, or at least it won't affect the primary bond. So I think if you mean it, maybe your meaning is if you print at higher temperature, you have a stronger part. And in one way, yes. Why? Because first you have less internal stress. The internal stress will create microfracture, and this microfracture will weaken your parts. But another reason is the layer adhesion. Where does layer adhesion come from? It comes from the number of entanglements you have between one layer to the other layer. So you are printing a pack of spaghetti. on top of another pack of spaghetti. The more spaghetti start to entangle each other, and the more force there is between these two packs of spaghetti. How can you make more entanglement? Well, the entanglement only happens when the polymer can move around easily in order to get entangled with other. How can you make a polymer move more easily? Then more temperature, above glass transition temperature. So the longer time two layers are touching each other above TG, the more entanglement you are going to have. And another factor is the pressure. The more pressure you have between two layers, and the more probability you are going to create entanglement between these two layers. So yes, printing at higher temperature will increase the layer adhesion, which will increase the feeling of having a stronger finished product. Back in a minute, gonna check on my violin print. Yeah, I'm looking forward to see that print, Brian. Hello everyone. Hello Patrick. Thank you for joining. I hope you didn't join in the middle of the warping explanation. Otherwise, maybe it didn't make so much sense. Loyal, that makes so much sense. Yeah, because you were here from the beginning of the explanation. Hi, Peter. Yeah, thank you so much, everyone, for joining this stream. Loyal, this is fantastic knowledge. Yeah, I mean, that's the knowledge we all have created together, right? Everyone is kind of experimenting in their own way, and having communities allow us to put all of our experiment, all of our knowledge together, and then it's all about creating some logic between all of these points, and then we end up with a massive knowledge that the community has created. Sounds like one of the problems I was battling earlier this week. Yeah, so hopefully, like I said, once you understand the root cause of the problem, then you can open up, the door to any solution that comes to your mind. The most important is understanding what's happening, and then after that is fine. I don't want to. Some people has warping problem, and I just tell them, okay, print at higher temperature. You don't need to understand why, just do it. No. I want, if people has warping problem, I just explain, okay, you have this problem because this and this and this. And then by themselves, they are going to say, oh, then I just need to do that. And then they just solve their problem, because they know their printer, they know their print, they know their slicer much better than I do. So I rather focus on explaining the root cause rather than what kind of solution could work for them. So I'm happy that this explanation may have opened some new solution to solve your problem. Loyal, compensating with higher polymer extrusion temperature. That's fantastic. Yeah. I mean, that opened up so many solutions. I'm pretty sure you guys have other solution in mind that I haven't mentioned yet. Santiago, would it be possible to co-extrude a filament with, let's say, a lower temperature PC in the middle with a higher temperature PC on the outside to flatten the curve? A lower temperature PC in the middle. Yeah, it is possible. But I would say it's a lot of, because you need, I mean, it is possible to co-extrude filaments, right? Company are already doing that. But I would rather focusing on having a nozzle that is able to heat up the material homogeneously instead of compensating by having different type of material within the filament. But definitely it is possible. Yeah, you missed the description, non-fan. Loyal, oh, that makes so much sense. Higher temperature, more entanglement. Yes. The violin is about 70% done. The printing should be done tomorrow. Then install the part. Yeah, looking forward to, and please take a video so that we can hear a little bit how it sounds. Collie Logan. I still don't know how to pronounce the name, by the way. I'm definitely going to have a go back and rewatch this one. Yeah. For everyone that joined in the middle, please try to go back to the beginning of the warping explanation so that you can try to follow. And I will get in contact with Loyal to learn about how to have so many cameras in the setup so that I can have a camera with a whiteboard. And then we can go through that again with some a whiteboard so that I explain. Or you guys can get the 3D Print General book. I wrote a material science chapter inside where all what I say, I explain it in that. Or you can also, I did a video in partnership with 3D Print General, and I did some animation where you can see exactly why, or you can see an illustration of what I just said. You can go and check in on Sean's channel, the 3D Print General channel. There is a material science video where I'm featured inside to explain a couple of things, and I think warping was one of them. So you can go and have a look. It might be easier than the way I explain it live. Collie, you are saying my name just fine. Collie? Okay, then I will just stay with Collie. Santiago, awesome. Thank you, Nicolas. Happy New Year, everybody. Yeah, I think we reached the end of the stream. I'm very sorry for the one that just joined. It's the 31st here. It's New Year's Eve here. So I'm going to go back home and prepare the big dinner for this evening. Thank you again, everyone, for joining. It was a lot of fun today to go into the warping explanation. I have a lot of oozing explanation. What's the difference between oozing and stringing? What's the difference between extrusion temperature, printing temperature, printing speed, and extrusion speed? I have a lot of things to share with you guys. So that was the last stream of Polymaker for 2021, and I hope I will see you in 2022. It was so much fun today, and I'm sure in 2022 we will have even more fun. Thank you again, guys. And Happy New Year.